Beautiful. Beautiful. So currently got 10-2 today. Got that due Tuesday. Tuesday, we're either going to review or do 11-1. There's only 2 sections per. Last year, I put 10 and 11 together. We'll kind of see how it goes, probably mostly from your perspective on Tuesday. But today's 10-2 no matter what. Estimating a difference in means. Estimating a difference in means. So really we're combining what, 9, 8, 9, 8, 2, and 9, 1. We're really kind of combining them together with a slight curveball. Conditions. I'll just throw you right into the conditions, right? You're going to have 2 samples. So 2 independent random samples, and both need to be less than 10% of the population. Again, these don't change. These don't change. These are the same for all of them. And then the large counts is also the same. We just need to make sure we get it updated on how we show the large counts or approximately normal. So we got 2 independent random samples. And this is going to be, like, that independent is going to be huge this chapter, because you might have some that are not independent. And so we're going to talk about that halfway through this lesson. So make sure you recognize if they are independent or not. Like I said, that's going to be huge. 2 independent random samples. Both of them have to be less than 10% of the population. Some of you guys are getting these mixed up with the 10% and the large counts. This has nothing to do with the large counts. This has to prove, this will prove that the standard deviation or the standard error formula works. That's what that proves, that the standard error formula works. So we need to sample less than 10% of the population. And of course, both of them have to be. And then the large count. So let's show we're going to have to do this. Each must fit the large counts. Each must fit the large counts. And if you can remember, for means, how we prove that is the population is normal, which that never happens. I don't think I've ever seen that happen other than maybe once or twice on my worksheets. Both of them fit the large counts condition, which is greater than 30. Both of them have to be larger than 30. Sample or samples is or are larger than 30. Or we'll have to graph the sample or samples. One of those 3 will happen, and again, this one hardly ever happens. So we got to, hopefully they're both bigger than 30. Hopefully, that's the easiest one. If they're not bigger than 30, they're going to give you the data and you have to graph it. One of them might be over 30 and the other one you might have to graph. Or they might give you both sets, but one of them be over 30. If one of them's over 30, you're okay here. If they're not, you'll have to graph it. So not a big difference. It's just everything's 2s. Independent random samples both need to be less than 10%, and both need to fit large counts, or both need to be approximately normal. So both either have to do that or that. Again, we've talked a little bit about that. I'm good with either one of those words. Really, large counts fits this, and then large counts doesn't fit this. This isn't approximately normal, but AP is okay with both. They kind of just call it the large counts condition or the approximately normal condition. Everybody okay with the conditions? It hadn't changed for any of them, right? 3 conditions, we got to fit them. Boom. Man, so I guess it looks like I jump right into it. A college student wants to compare the cost of 1 and 2 bedroom apartments near campus. She collects the following data on monthly rents in dollars for a random sample of 10 apartments. Dadgummit, she didn't get 30. So we're going to have to graph those 10 and graph those 10. The easiest way I think to do that is like put one of these in L1 and put one of these in L2 and just graph them both at the same time. Second y equals, turn one of the graphs on L1 and then turn another graph on L2. Zoom 9 it, and it shows both of them. Okay? Mu be the true mean of 1 bedroom, and mu 2 be the true mean of the 2 bedroom. Check to see if the conditions are met. She collects the following data on monthly rents for a random sample of 10 apartments of each 10th random sample. So we have, I don't know how independent they are, but I'm guessing they're independent. A random sample of 10 apartments of each type. 2 independent random samples. I'm guessing they're both less than 10% of all apartments. There's only 10 of them, so maybe there's 100, I don't know, but we go with that. And then we got to graph those bad boys and graph those bad boys. Put one of them in L1, put one in L2, second y equals, graph the first one, graph the second one. We got to turn those graphs over on our paper. Sketch, it doesn't have to be beautiful. And that's why box and whisker is the easiest. Independent random samples of 10. We can assume that 10 is less than 10% of one bedroom and 10 is less than 10% of all two bedroom. Again, be a little bit more precise on checking these conditions. 2 independent random samples, 10 one bedroom, 10 two bedroom. 10 is less than 10% of all one bedroom. 10 is less than 10% of all two bedroom. Now you can say 10 is less than 1 and 2. And then we'll have to graph, they've graphed, again, dot plots. I don't think, to me, it's easier to do box and whiskers than it is dot plots. There's only 10. It's going to really hard to be bad data. Questions? I'm just kind of going through that pretty quickly. Do I need to show that on the calculator? Anything? Okay. Second y equals, turn the first one on. I turn off all my graphs first. Turn off all, especially your pre-calc kids, because I know y'all are starting to use a lot of those graphs. So I just turn off all those y equals graphs. So just clear all those out. And then second y equals to turn your plots on. Zoom 9. When you go back to pre-cal, you'll want zoom 6. That does 10, 10, 10, 10. Or anybody else that's using them for something else, 10, 10, 10, 10. So zoom 9 for this class, zoom 6 for everything else, and then sometimes you got to move them around. Formula, still those words. We got to turn them into values. So our statistic now, we have 2 of these, x bar 1 minus x bar 2. We always want the difference. We don't ever want the sum, right? We want to know the difference between 1 bedroom and 2 bedroom. We want to know the difference of males and females. Don't care what it is. We just want the difference between it. Plus or minus, it's still going to be, whoops, a t critical value. It's still going to be t's. Every time you're dealing with means, you're dealing with t's, not z's. And then the standard deviation of the statistic is starting to get kind of nasty. We have to square the first one and divide it by n1. And then you have to square the second one and divide it by n2. Because we should know that we always have to add variances. So we have to add variances, and then we'll take the square root back out of it to get the standard error. Let's see if I did that for good. Yes, beautiful. Again, we can put the star there or not put the star there. It's not that big a deal. Y'all okay? Good. Questions there? This is found the exact same way we did 10-1, either inverse T or special program or table. The degrees of freedom. Oh, no. Here's the degrees of freedom. It's different. It's a different formula. It's not on your formula sheet. And I'm not kidding. This one's bad. When will you use this formula? Never. Never. That's the formula that your calculator uses when you punch all the stuff in and you do 2 samp, or it says what? I think it says 2 t interval or something. We'll have to look at it, see what it says. But that, when you do all that stuff and you hit enter, you're going to get some weird number for your DF. It comes from this. You don't ever have to use it. You don't have to know it. You just have to know why is it a little weird. You don't even have to know why, but you need to understand why it's a little different. And it's because of this crazy formula. Again, you won't ever use it. All you'll put down is DF equals whatever it equals. Okay? If you are ever asked for the DF without the information, this is what your calculator will do. You do not have to show it. You do not have to do anything with it. I just wanted y'all to see it. But there is a conservative option that you may or may not use. And it's the smaller of the n minus ones. The smaller of the n minus ones. Don't use it very often unless if you just have to. If you can't use your calculator, okay, I'm just going to tell you, if you can't use your calculator to find the DF, it happens once on your homework, I think, maybe twice on your homework. That's the only time I've ever seen it. If you can't use your calculator to find it, in other words, you don't have the data, they didn't give you anything else, you can't calculate it from your calculator, then just use the smaller of the n minus ones. Use the smaller of the n minus ones. That's a conservative. Kind of like using 0.5 inside the radical, right? That gives me kind of the worst case scenario. That gives me the widest possible. The DF that they're going to give you is a little bit more narrower than that. Use the smaller of the n minus 1. That's why it says n2 minus 1 or the n1. The smaller of those two. With this option, resulting confidence interval is larger than any, whatever. You're going to use option 1 most of the time because your calculator is just going to give it to you. So DF equals whatever the heck, and it's going to be a decimal. It's going to be nasty, as you can possibly tell from all this stuff going on. Basically, it's the variance squared, n minus 1, and then that variance, I don't know. I don't know why they get that. Wade Track Preserve, Georgia's Old Forest Pine. Well, one question of interest. How do the sizes of the long pine trees in the northern and southern halves for the forest compare? To find out, researchers took random samples of 30 trees, thank you, from each half, measured the diameter of at breast height, DBH, that's actually something called, whatever, in centimeters. Here's the summary statistics. So both of them are 30. Here's the mean of the northern group. Here's the mean of the southern group, quite a bit larger. There's the standard deviation of the northern. There's the standard deviation of the southern. For some reason, they graphed both of those two. I don't think I care about those graphs because they're both 30. I don't even know what they're at. They didn't ask anything yet. Oh, based on the graph and the numerical summaries, write a few sentences comparing the sizes of the long leaf pine trees in the two halves of the forest. We're starting to dig up a bunch of stuff from first semester at some point. We're starting to do that. When I have to write a few sentences comparing, we better compare 3 things. Shape, center, spread. Better compare those. And then if there's anything weird, right? And I don't think there's anything weird. Shape of the northern is somewhat skewed to the right, a little bit, while the shape of the southern is skewed to the left. And I'm just getting that from these. This tail is longer than this. This tail is longer. This tail is longer. So I'm thinking it's slightly skewed to the right, slightly skewed to the left, but not a whole lot. Just don't lie. So that's the shape. The center or the middle of the northern group is smaller than the northern group or the southern group. The center is smaller for the northern group than the southern group. You don't have to say what they are, you just have to compare them. You can remember, I think that was chapter 1 or chapter 2. And then the spread or the variance or the variation, or you could say standard deviation, is larger for the northern group than the southern group. Again, you don't have to give numbers, you just have to compare larger, smaller. If you say the northern is 23.7 and the southern is 34.5, they're going to ding you because you didn't compare. You just told me what they were. So and then make sure we're in the context. The shape of the northern tree. So let's see what we put. Shape. The distribution of DBH in the northern sample appears skewed to the right, while the distribution of DBH in the southern sample is skewed to the left. They didn't say anything about outliers. You don't have to. If there's nothing there, you don't really have to say it. It appears that the trees in the southern half have a larger diameter. The mean and median are larger. They said both. Here's the mean, here's the median. Compare either one. Compare either one. It would be really weird if this mean was smaller and that median was larger. But if that happened, you'd probably say that. Variability. There's more variability in the northern than the southern because the range and the IQR and the standard deviation are all larger. You really only need to compare one. But let's kind of go back, right? Here's the range from min to max. So it's larger here than this, not by much. Those are pretty close. The IQR comes from the box. This one is larger than this one. And then the standard deviation comes from here. And you can, any one of those three describes the spread. You don't have to talk about all three. You got to talk about one of them. And you could just say spread. The spread is larger for the north than the south. The variability is larger for the north than the south. Okay, y'all okay with that comparing? Make sure we remember that. Coming up, beautiful. Construct and interpret a 90% confidence interval for the difference of the mean DBH. So here we go, construct and interpret. 2 independent random samples, 30 north, 30 south. Good enough. Good enough. That proves it. 30 is less than 10% of both north, south. Whew. 30 greater than or equal to 30. 30 greater than or equal to 30. North, south, approx normal or large counts. Don't care. Large counts. That'd be a little iffy right there. Lidkins. Large counts. Okay. X bar 1 minus X bar 2 plus or minus T square root S squared 1 in 1 S squared 2 in 2. Plug and chug. Plug and chug. 23.7 minus 34.5 plus or minus T square root 17.5, 30 plus 14.26. Oh, those are squared. Oops. 30. Beautiful. Boom. Whoops. I need this. Boom. Boom. Exit. Let my calculator do all the work. I don't want to do any of that. Stat tests. It's not a test, it's an interval. It's not a z interval. Oh, there's where it says 2 samp t int. That's what it says. That's what I thought it said. 2 samp t int. Ooh, that's the method. I probably should write that. Right? I didn't write the method. I don't have to because I wrote the formula. But if you want to feel good, write that. I don't have the data, I have the stats. Don't have the data, I have the stats. So X bar 1, boom, help me out, 23, 7, 17, 17.5, 30, I remember that one. I don't remember. 34.5. 5, 3. 12? Shucks. 14.26. 30. Was it 90? 90? Never pool. Never pool. Pooling is basically you're combining the data together. We're not combining the data together. So it's never pooled. Calculate. Boom. There's the min, -17 to -3. There's your DF. Okay, that's that weird formula. They did not use 29. So don't put 29 because 29 is going to give you a different interval because it's going to give you a different T critical value. So if you're wanting to put the T critical value, make sure you use 54. Oh no, I guess you use 55 as a DF. Sorry. I don't ever put it. You don't have to put it. You noticed that, right? When I went from the formula to the numbers, I didn't put a number in for T. You don't have to. So there's the DF, but you do need to put down what DF is. There's X bar 1, there's X bar 2, there's S of X, there's N1, N2, there's everything else you need. Please let your calculator do that math. Don't try to be a hero or a stud and try to punch all that stuff up and hit enter. Don't. Let your calculator do the math. -17.7, -3.9. Notice it's negative because I put the northern first and the southern second. It was larger. It's okay. If you don't like that, switch everything. You can switch everything and it'll be positive. It'd probably be +3 to +17. Beautiful. I won't remember that. 17.739. -17.7, -3.9. We are 90% confident that the difference in the mean DBH of longleaf pines in northern and southern halves of Wade Tract Preserve. Let everyone tell you what to put. That's your context. Is between that and that. Or, I guess, the interval. We are 90% that the interval from here to here captures the true mean DBH of all. But that's why you can say true. Beautiful. Any questions about what you need to put or what you don't put or what I didn't put or what I did put? Hit me. DF. Oh, yep, -1. Cuss. Thank you. Told y'all. What was it? 55 point what? 7? If you just want to put 55, I don't think I'd put 56. That's why I just put 55.7. Cuss. Thank you. -1. Told you. That happens. You got your calculator to look right there, though. You're putting all that stuff. Right? You're putting all that stuff because that's what I put. All that stuff's labeled. You don't have to put that formula, but if you don't put that formula, you better have two sample mean difference, T. Right? The method. You either have to have the method or you have to have the formula. But if you don't put the formula and you put the method, you got to tell me what X bar 1 is and what X bar 2 is. And that's okay. You can do all that and you can just list it down that way. X bar 1 equals X bar 2 equals. You can do that. That's okay. But you can't have just the method and that interval. You got to label what X bar 1 is and what X bar 2 is. And that's why I go from here to here, because that's obvious what each one of them are. You don't have to tell me what T is. I used to make students do it, and then I told them they don't have to, but I'm just changing that up this year. And just, you don't have to do it. It's not part of the rubric on the AP. If you do, use it. Just make sure you use 55 as your DF. Don't use 29, because if you use 29 and you put that there and you get that interval, they will ding you. They will ding you because you used a different number that gave you you lied. You lied. That's using a DF of 55. Let's see how he did. There's where they did the method. 90% confidence interval for mu1, mu2, mu1. They defined everything. They're just trying to keep consistent with Hose and Haas. I don't do this. It's not a requirement. Plan, 2 SAMP T interval for mu1 minus mu2. Okay, that's a method. Random, independent random samples of 30 trees from the north and south. Beautiful. 10%. Assume 30 is less than 10% of all north and south. Beautiful. 30 is, oh, here we are. 30 is greater than or equal to 30. So we're good. N2, greater than or equal to 30. They put normal large counts. Okay, they did both. Whatever. Check. You just got to make sure you get it all done in there. And you don't have to do it first, right? You just got to make sure you list it all. And then here's where they didn't write the formula, but they just told me X bar 1, X bar 2, S1, S2, N1, N2, using DF of 29. There's the T critical value. I hope their interval is different than ours. Oh, they flip-flopped everything. But those are different values, right? Because they use 29. That's why I want to make sure you know that if you're using 29, you're going to have to punch all that stuff up in your calculator because that number is different for 29 than it is for 55. Y'all okay with what I'm saying, right? That number is different for 29 than 55. So if you're using 29, you're going to have to punch all that stuff up because your calculator used the 55. You don't have to put that number. Just put T down again. We are 90% confident the interval from there to there captures mu1 minus mu2, whatever, the difference in the true. Did I say difference? I don't know if I said the word difference. Did I even write it? Did I get lazy? I didn't even, I just said it. Oh, I didn't say difference. Oh, the true difference in the mean. Sorry. We might make sure we capture the difference. We didn't capture the true mean of Longley. We captured the true difference of the means. Minus 2. I missed 2 out of 10. 80. Yes, ma'am. So we did northern minus southern. So we want to say it that way. They did southern minus northern. You want to say southern minus northern. Does that answer your question? No, it does not matter. It does not matter. They do not care because everything's labeled. That's why you have to make sure you label what X1 is and what X2 is, right? X1 was southern, this was northern, or vice versa. Northern, southern. And so I want to say northern minus southern. And if you flip-flop everything, you flip-flop it, it's okay, but you're just going to have positive numbers. And that's why you have to label stuff. Good question. Anybody else? Questions about where we're going to get all of your points? 10 points. 10-point question somewhere in there. And I just kind of start looking to see how many points you deserve minus. I would have gotten minus 2 because I didn't put the difference and I didn't put DF. So I would have got 8 out of 10. Bad teacher. It's okay. 8 out of 10 is probably still a 5 or a 4. It's a B. We don't like B's. We like A's and we want 5s. Here it is on the calculator. Always choose no for pooled. Pooled means you're combining data together. We're just not doing that. We just don't do it. So we just always say no. Beautiful. Okay. Any questions about that? Now, here's our curveball. Here's our curveball. All right, so comparing two means, and then they're going to talk about paired data. Paired data. So basically, I'm throwing in your head already, these are not independent random samples. They're not going to be independent random samples. And it's sometimes hard to see the difference between independent and non-independent. That one definitely was, although I don't know how you can pair those northern and southern trees up. A researcher studied a random sample of identical twins who have been separated and adopted at birth. In each case, one twin, A, was adopted by a high-income family and the other twin by a low-income family. This is interesting. Both twins were given IQ tests as adults. So here's twin A. Here's twin B. This is the pair. So A and B, A and B, A and B. And I don't know which one was, oh, I guess A was the high income and B was low income. 128, 120, 104. It looks like A is doing a little bit better than B. However, do recognize this 128 has nothing to do with that 97 over there, right? Because they're different twins. So I'm trying to compare if there's a difference between each one of these as opposed to whatever the heck X bar is over here and whatever the heck X bar is over here. I don't care about the average of all these and the average of all these. I care about the difference between each one of those. Kind of follow what I'm saying, right? This data is not independent because this twin and this twin are kind of paired up. They're kind of paired up. This is not really independent. These are independent, but these are not. Okay? The previous analyst ignores the fact that these are paired data. Paired data results from recording two values from each individual. Two values from each individual. That's not what happened here. You'll see one of these examples in just a second. Two values from each individual, like a before and after. I record your typing speed before, and then I record your typing speed after the typing class. I'm not too concerned with all of them. I'm concerned with each individual improvement. Or a pair of similar individuals, which is what we did this time. Okay? The northern and southern trees, they were not paired. I guess I could have paired them by when they were planted. I don't know. We're doing a whole lot of extra work there. It didn't talk anything about that. So sometimes you can pair data, but it would specifically talk about how they're paired. These are the most common things. You're getting data from the same individual, so basically it's paired with themselves, or a pair of similar individuals. Okay? It's a pretty hard thing to recognize when data is paired or when it's not. So just kind of read and be careful about that. Everybody okay? We're ready to go on? Talk about it? When we have this, we are interested in the mean difference. We are interested in the mean difference. Think about what that is here. The mean. Well, the mean is the average. The average. The average of the differences. The average of the differences. 1x bar. 1x bar. The average of the differences. That is different than what we were doing earlier, because we weren't doing the mean differences. We were doing the difference of the means. That's the difference of the means. That looks like pith. That's the mean difference. English. Ugh. Kind of see that. Mean difference. Mean difference. Difference of the means. When you see difference of the means, it's two samples. When you see mean difference, it's one sample. And it's not really one sample, but you're making it one sample. Okay? This is the key. When you read mean difference, you should be thinking paired data. You should be thinking paired data. Mean difference. I don't want the difference of the means. I don't want X bar 1 and X bar 2 and the difference between those. I want the differences and then get the X bar of those. Yes. Click, 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 click. This is not the same as the difference of the means. When we pair data, essentially it becomes one sample. When we pair data, it essentially becomes one sample. We are not interested in the difference of the means, but the mean difference. And just write it like it says, and you'll be less likely to mess up. Mean difference. Difference of the means. Difference of the means. That's your clue. Never will they say difference of the means and want this, and never will they say mean difference and want that. And they will say one of those two. So those are kind of your clues. So when we have data like this, you need to recognize it's paired. Okay, and again, it will say mean difference. The way that I do this in my calculator is you can either subtract these in your head really quickly. This is not too bad. But if you don't want to do that, put this in L1, put this in L2, and then in L3. So L1, you have 128, and you have 104. In L2, you have 120, and you have 99. And then in L3, you can go up here to L3. You can go up to L3. And then you can type in L1 minus L2, and it will subtract them all for you really quickly. I'll show you that in a second, or you can just subtract them, whatever you got to do, and then put those in L1 or L2 or L3 or whatever you want to. Whatever you got to do, you got to get these darn differences. However you got to do it, you got to get the differences. However, and then once you have those differences, we're on Tuesday's lesson, because it's essentially one sample. It's essentially one sample. I don't care about what this is, and I don't care about what this is anymore. I'm done. Once you figure out the differences, don't even go back to these. Just look at the differences. So there's a difference of A minus B. Yes, there is a negative one. Okay, we're going to have some negatives. You're going to have some positives. Okay. There's a graph of the differences. I don't care what this graph looks like, and I don't care what that graph looks like. Why did I have to graph the differences? Because there's only 12 of them. If there were 30 of them, I wouldn't have to graph them. If there were 30 of them, I wouldn't have to graph them because I had fit the large counts. But I don't fit the large count, so I need to graph it. And again, they use dot plots. I use box and whiskers because it's a whole lot easier. So second y equals, go to wherever you put the differences. Don't look at L1, don't look at L2, look at your differences. But if you put the differences in L1, then just look at L1. The mean difference will be 5.833, but your calculator is going to give you all that information. You don't have to figure that out, right? Because you're going to do one sample. It's just going to be what you guys did on Tuesday. Second, or stat tests, go down to T interval, because it's still T's, it's means. And then your data is going to come from your differences. Very few times do they not give you all of the data. Most time they have to give you all the data so you can find the difference. There's the standard deviation of the differences. Notice they're doing like sub-difference. That helps you. It's not required, but it helps you. It helps you. So X bar sub D, X bar sub diff, S bar sub D, S bar sub diff. It just helps you. It's not required, but it helps you. There are two ways statistical study of a variable can yield paired data. We kind of talked about this already, right? Two values from each individual, a before and after. That's always paired. That's always paired. Experiments investigating whether music helps or hinders learning. That means what? What am I looking for when I say that? When you see this experiment, we have to not check the 10%. Okay, don't check the 10% on that. And then there are a pair of similar individuals. Those are the ways that's the way it's paired. But you're not going to care, guys. Mean difference. If you see that, it's paired. It's paired. Mean difference. Here's your conditions, and you already know these conditions because they're the exact same conditions from Tuesday. The paired data comes from a random sample. We somewhere or another, we got to start talking about this stuff being paired. We have a random sample of paired data. Whatever. Now, this one you got to be careful with because a lot of times these are experiments, right? We're using all of them. We're using all of them. If it's a sample of them, we're always using all of them though too. So just make sure if it's not assign it. It's not randomly assigned. Okay, so just be careful with that. And then large counts. And again, all I care about are the differences. All I care about are the differences. I don't care about what L1 is. I don't care what L2 is. I don't care what X bar 1 is. I don't care what X bar 2 is. I care about the differences. So the differences need to be greater than 30. Hardly ever happens. You typically have to graph the differences. Graph the differences. And wherever you find the differences. Wherever you find the differences. The hardest thing about this is reading mean difference instead of difference of the means. Difference of the means. Let's go back real quick just to emphasize that. Difference in the means. Difference in the mean. That's two samples. They don't say anything about it. This was leading me into it. Beautiful, 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 beautiful. Your formula is one sample. It's one sample. If you want to put the sub differences, you can, but you don't have to. Again, it's just one sample. It's X bar plus or minus T standard deviation over the square root of N. Sorry, shouldn't have an N1. If you want to put the sub differences, that's one of those things that really tells that grader you know what you're doing, but you don't have to do that. You don't care. I mean, they don't have to. It's just one sample. It's one sample. Your degrees of freedom is N minus 1 because it's one sample. It's one sample. So it's N minus 1. And you know, that's the one that I told you is really hard. You had, yeah, right? N minus 1. N minus 1. Here it is. Here's my paired data. Random sample of identical twins. That should somewhat clue to you right now. Following table, construct and interpret a 95% confidence interval for the true mean difference. So what it's going to say, you got to recognize it. Mean difference. Mean difference. So I got to figure out what those differences are. You can go through it manually, or like I said, put those in L1, put those in L2, and then you can do the differences in L3. I don't know what way's easier. I mean, you got to punch in some way or another. You got to get those differences. A lot of these you can probably do in your head. It's probably just easier to subtract them in your head and put those numbers down. However, if you mess up something, that could mess up X bar and all that. Let me show you on a calculator real quick, just to show you the options you have. Come on. Stat, edit. Okay, so you got to have the same number of data. Like I can't go over here and do L1 minus L2 because it's going to give me errors because I don't have equal data. But you would just go up there and do second L1 minus second L2, and that will subtract them all for you. Error. Yeah, see? Dimensions mismatch. Go to. Yeah, it's just telling me I can't do that because I don't have that. But then all I'm going to do, everything's L3. You're going to graph L3. You're going to do T interval with L3. And then when you do that, it's going to give you X bar. It's going to give you the standard deviation. because you're going to go stat and you're going to go test and you're going to go T interval. And you have the data now. And this is wherever you put the differences because it's just one sample. So wherever you put the differences, and when you do that and you calculate it, it gives you X bar and it gives you the standard deviation. It does all the math for you. You just got to put it down on your paper. Beautiful, beautiful. Keep slideshow. Beautiful. 95% confidence interval. Again, I don't do the state. One sample T interval. One sample T interval for mu. Somewhere you just talk about the differences. One sample paired data. We have a set of paired data. I don't know, however you want to say it. Paired. Random sample of 12 pairs. Beautiful. Assume that 12 is less than 10% of all pairs of twins. And I had to graph the data. There it is. The differences, again, we got to use those. We got to keep using that word. Differences is small, but the dot plot does not show strong skewness or outliers. That's just what I say every time. No strong skewness or outliers. The box plot looks approximately normal. There's X bar sub D, there's S sub D, there's N sub D. DF is 11. Remember, you got to put DF. There's the T critical value, but you don't have to put that. There's X bar, there's the critical value, there's S sub X, there's N. One of the tricks they like to do on multiple choices is they like to put DF right here. They like to put square root of DF on the bottom. That's a trick on their multiple choices. Just be aware of that. You don't have to show that step. There's the interval. We are 95% confident that the interval from there to there captures the true mean difference. Just make sure you attribute to the mean difference. And guys, go back to what it says. Captures the true mean difference. They're going to tell you what to put. Put it. Use that. Because if you don't say the words mean difference, they're going to ding you. They're going to ding you. Yes, no, maybe. I didn't go through everything, but I don't know if I have to. I don't want to waste your time a whole lot. Determine whether the conditions are met for a difference between two means. Construct and interpret a confidence interval for the difference between two means. Analyze distributions of the differences in paired set and graphs of summary statistics. Construct and interpret a confidence interval for the mean difference. Your homework should be posted. Should be posted.